Hey class, welcome back. Today, in this video, we're going to introduce the idea of kinematics in one dimension, which means the way in which we describe motion and talk about motion, starting with the example of just one-dimensional motion. So what is kinematics? Well, kinematics deals with anything we need to describe motion, the way in which we describe things moving. All right, that combined with dynamics, which is looking at what the way in which forces affect motion, those two things combine together to make the field known as mechanics. So any of you interested in becoming mechanical engineers, hopefully you like kinematics and dynamics, because that's a huge majority of what goes into the field of mechanics and the field of mechanical engineering. All right, so how do we describe motion? Think for a minute to yourself. What is it that we use to describe motion? What sort of physical quantities and units might we use to describe motion? One is displacement. So displacement is looking at the change in position of an object. So let's say we have this car at some time t equals 0. It's at an original location we're going to define as the origin, or a location we're going to define as x sub 0. At some time later, it's at a final position we're going to define as x, and so its displacement is just the change in x, the difference between where it started and where it ended up. And so the way we express displacement is its final position, x, minus its initial position, x sub 0. And that is displacement. Pretty straightforward. So keep in mind, displacement, we need to pay attention to its sign. All right, whether it's positive, you can have positive displacement or negative displacement, as we'll talk about in more detail next chapter when we begin our discussion of vectors. All right, so in this case, if we have an initial position of 2 meters, a final position of 7 meters, then our displacement was 5 meters in the positive direction. Now, if we were to return to our original position once again, we would have again a displacement vector with a magnitude of 5 meters, but now it's in the negative direction since we ended at the location of 2 meters and we began at a position of 7 meters, then our displacement is negative 5 meters. So those two displacements are not the same. One is positive and one is negative because of the different direction. So, next thing we care about in addition to displacement is speed. How fast are we moving, right? So the average speed that something is moving at is equal to its distance divided by its time, which that makes sense, right? If you run a 40-meter dash in 5 seconds, then your average speed would be 40 meters divided by 5 seconds, or 8 meters per second, while running the 40-meter dash. I think it's a 40-yard dash, but we'll do it in meters. So the SI unit is distance over time, so meters over seconds or meters per second. That's the SI unit for speed. So let's practice this really quick. Imagine, I grew up in Reno, so imagine we are taking a road trip to Reno. Reno is 550 miles away. If your average speed while driving to Reno is 25 meters per second, how many hours will it take you to get there? Keeping in mind that 1 mile is equal to 1,609 meters. All right, so make sure you pause the video, give this one a try, and let's see if you can get it right. Just so you know, here's the route that we take. All right, so here we have, again, average speed is going to be equal to change in position over time. Solving for time, we find that time is equal to change in position divided by our average speed, and plugging in our values after doing a unit conversion from miles to meters, we find that we traveled 885,000 meters at 25 meters per second, so it would have taken about 35,400 seconds, or 9.83 hours. Again, a box-worthy solution. All right, so that's speed. Sounds good. Average speed, got it. Now, velocity is slightly different than speed. Velocity is not only speed, but also the direction that you're going. So speed is just how fast you're going. Velocity is how fast you're going and in what direction. So we define average velocity as being equal to the displacement divided by the elapsed time. not the change in position, or just the position, but the displacement over elapsed time. The way that we write that is average velocity equals change in position over change in time. If we want to know the velocity not at an average, but at a specific instant in time, then we're going to look for the instantaneous velocity. An instantaneous velocity, or what we normally would just refer to as v, is going to be the average velocity over a very short period of time. Well, what does it mean to look at a very short period of time? Well, that's the same as taking the derivative. So the way that we define velocity, sometimes referred to as instantaneous velocity, is just the derivative of your displacement vector or your position vector with respect to time. So the derivative of position with respect to time is velocity, which, to bring back the good old days of Calculus 1, that means that the velocity is the slope of the position versus time graph. So it's the slope of the position versus time graph at a single point, which is something we'll investigate in our next lab. So here's an example. We have instantaneous velocity at various different points, a graph of position versus time, and I want you to consider the instantaneous velocity at various different points. So first of all, I want you to tell me, where is the velocity 0? So you have four options: point A, point B, point C, and or point D. Where is the velocity 0? Where is the velocity constant? And where is the velocity changing? Write it on a piece of paper, pause the video, and then we'll check. Okay, so let's see what you got. The velocity is 0 when the slope is equal to 0, when we have a flat horizontal line. So that means both at point A and up here at point D, we will have a velocity equal to 0. Where's the velocity constant? Well, that's where the slope is constant. So we have a constant slope all the way from point B to point C. In this section, we have a constant slope, so therefore we have a constant velocity. And where is the velocity changing? Well, that's when you have a changing slope. All right, so here we have a changing slope from A to B, and here we have a changing slope from C to about D, maybe a little before, but we have those points, so that would be where it's changing. So what would a graph look like? Oh, apparently my graph didn't want to show up. Let me see if I can fix that 1 second. Okay, there's our graph, and now you can see again what the velocity versus time graph would look like relative to the position versus time. So here's an example problem for you where you can practice trying to determine the velocity in different situations. So here we have a high-speed vehicle that's set at one point the world land speed record of 341 meters per second. This was back in 1997. All right. To establish the record, the driver has to drive 2 different directions. He has to go, turn around, and come back. All right, driving a mile in each direction. The reason they do that is to nullify any effects due to wind, and they take the average of the two. So as you can see here, the first length of 1 mile going from left to right, or in what I'm going to define as a positive direction, took 4.74 seconds. Going in the opposite direction took 4.695 seconds. And so I want you to use this data to determine the average velocity of each run. Pause the video, try it out. All right, so let's see what the solution is. Again, average velocity is just going to be change in position over time. So in the first leg, part A, it had an average velocity of 339.5 meters per second. In part B, it had an average velocity of 342.7 meters per second in the negative direction, hence the negative sign that we see there. So those are the average velocities. All right, so the last thing I want to introduce to you is acceleration. What is acceleration? Well, it's change in velocity with respect to time. It's the rate at which we're changing velocity. If you're accelerating in your car, you're going faster and faster and faster, or slower and slower and slower if it's a negative acceleration. So acceleration is defined as the change in velocity with respect to time. So average acceleration is your change in velocity with respect to time. Instantaneous acceleration, can you guess? Think calculus. Sure enough, instantaneous acceleration, or what we're going to most commonly refer to as just acceleration, is the second derivative of position with respect to time, which makes it the first derivative of velocity with respect to time, as you can see here. All right, so graphically, what does this look like? Well, again, the slope of velocity versus time graph is your acceleration. So looking at that same graph that we had on a slide earlier, here's velocity versus time. All right, when on this graph are we going to have zero acceleration? When are we going to have a positive acceleration? And when are we going to have a negative acceleration? Again, think about it, write it down, and then we'll talk about it. All right, so we have an acceleration of 0 anytime our slope is flat, or 0 for our velocity versus graph. So down here at point A, also from B to C, and also at point D, we have 0 acceleration. We have a positive acceleration when our velocity is increasing, so that would be from time t equals 1 second to time t equals 3 seconds up here at B. And we have a negative acceleration when our change in velocity is negative, from C at 8 seconds down to 9 seconds. So what would a graph of acceleration versus time look like? There you go. All right, so I hope that's given you a good introduction to position, velocity, and acceleration. We'll continue to talk about these and learn more about quantifying them starting in class on Friday. Hope you all have a box-worthy day.